Okay, zeros of the numerator. Emma, what are the zeros of the numerator here? Good, only one of them, and it's x equals 1. Zeros of the denominator. So x equals -5 or x equals, yeah, that's a little strange one, right? I mean, is it going to be 1 or 0? 0. Here's a way I could demonstrate that for you. If we evaluate the function, let's evaluate the function at 1. If I evaluate the function at 1, when I plug 1 in for x, in the top I get 0. Right? On the bottom I get 6 times 1, which is not a 0 at the bottom, is it? Right, I got back 6 on the bottom. Does that make sense? If I evaluate this at 0, I get back 0 minus 1 is -1 over 0 plus 5 is 5 times 0, right? So that is a 0 at the bottom, okay? Okay, so the answer was -5 and 0. So what does that tell me? Answer some questions for me then about this function up here. So I want to know a couple things. I want to know what the domain is. I want to know where there are any vertical asymptotes. Any holes, and any x-intercepts. Okay? So the domain. What do you think, Manuel? What's the domain? Before you answer though, let's just kind of review our thinking on this, because it seems like when this question gets asked, I can sense that people aren't always sure how to deal with it, how to answer the question, where to start. Remember, the domain is just a set of all of the x values that I can input into the function. So normally, the default setting would be everything, right? All reals. And then we just got to kind of look for, okay, so that's the default, but are there any exceptions to that rule? Are there any places where I would violate one of my two rules? Taking an even root of a negative number or dividing by 0. Okay, so, then what do you think? Well, okay, so we'll start off by saying all real numbers. But are there any values of x that are going to cause us to have to divide by 0, for example? We sort of already answered that question in a way. If you just look at this, all the questions that I'm asking too, and I'll give you one hint here, and this is important to kind of recognize, that these questions, you don't even have to look at this sometimes complicated looking function there. We already did all the work we need. Everything you need to answer these questions is in that box. You can just ignore the function for now. We already did all the heavy lifting. So are there any values that are going to be excluded from the -5 and 0? Right? Because those are values that force us to divide by 0, right? So our domain would be all reals except x cannot equal -5 and x cannot equal 0. Okay, good. Tyler, any place where you would expect to find a vertical asymptote or vertical asymptotes? Based on what we talked about yesterday. Okay, yeah, so what about the denominator? You're right, it has to do with the denominator, doesn't it? 0? Okay, the zeros of the denominator, right? Okay, you're right. In this case, that's right. Now let's review. Let's review our just thinking about this. Vertical asymptotes for a rational function are going to occur specifically when? Based on the numbers that we would fill into this box for any problem, where are the vertical asymptotes going to be? What do you think? Where are vertical asymptotes going to occur? So, could be a different problem. We're using this function, but later on we'll do different functions, but we'll still fill in a box like this up here, right? Based on the answers in this box, where are the vertical asymptotes going to be? Say it again. -5 and 0 this time. But how come is my question. Why is that? What tells you that those are the places where we're going to definitely have vertical asymptotes?
Zeros of the denominator.
Okay, those are zeros of the denominator, but not the numerator, right? Remember that from yesterday? Okay, so those are the places, right? We're going to get vertical asymptotes at x equals -5 and x equals 0. And it's not an accident that those are places where x values that are restricted from the domain, right? If we look at a picture of this, and let's do that. Let's look at a picture of this function. So we got on the top x minus 1, and on the bottom, what do we got here? X, I'll just put the x, well, I'll do that. X plus 5 times x. Okay, so, so look at these features now, these vertical asymptotes that we get at -5, you said, and at x equals 0. If we zoom out, I mean, if we think about this in terms of like the landscape that an ant is walking on, right along the board, those vertical asymptotes are excluded from the domain, right? Those are x values the ant could never get to. Well, what's the math god's way of making that happen, right? The rules are the ant can never go to -5 or 0. What did they add? What kind of features did they add to this landscape to ensure that that happens? Well, we got these infinite walls, right? When the ant bumps up as he's walking from the left to right, when he gets close to x equals -5, he can't get there, so he's just gonna go down forever, right? And as hard as he tries to get closer to -5, all that's gonna happen is he's gonna go further down and get incrementally closer, but he can never get there. Just like I can't get to the door. I don't know how many times we've done this example, right? But if I cut my distance in half every second, I'll never get there, right? I'll just get closer and closer and closer. Same thing at 0, right? We've got these infinite walls, and if we zoom out, you can see that these asymptotes really just dominate the behavior of the function. When you zoom out, that's all you see are the asymptotes. And in fact, we haven't talked about this yet, but we can see we've got this blue vertical asymptote, right, at -5, or at, what was it, 0, yeah, -5. We've got this green asymptote, vertical asymptote at 0. Do you see another asymptote up there too? And think about the definition of an asymptote. An asymptote is just a line that describes the large-scale behavior of a function. So we got these two vertical asymptotes. Do you see another asymptote up there that's not vertical? Yeah, there is. If you zoom way out, doesn't the function also look like it's guided by a horizontal line? We haven't talked about how to find those yet, but there is another one. And if I had those 3 asymptotes, that describes most of the behavior of that function, right? So you can see why they're so important, okay? Okay, so what happens though, go back to this problem. So we had vertical asymptotes at -5 and 0. Any x-intercepts? Which would just be zeros of the function, right? X-intercepts are just places where y, which is f of x, is equal to 0. 1, yeah. And why is that again? Looking up here at the box, y is 1. Why can we look at those numbers up there and say, aha, 1 is an x-intercept? Because it's, how'd you get that answer right? Because 1 is a 0 of the numerator, but not the denominator, right? Are there any holes? Not this time, right? Not this time. Let's look at an example where there would be a hole. This guy, right? So this changes the list slightly. So what are we going to get? Kylie, what are the zeros of the numerator this time?
0.
Say it again.
0.
0 and 1. Okay, good. X equals 0 and x equals 1. And the zeros of the denominator, Cassidy?
-5 and 0.
Okay. Okay, notice this time we've got a 0 that appears in both lists, right? What's my domain gonna be? What's my domain? Everett, what's my domain? Up there.
Or just 5 or -5 and 0.
And 0, good. So those are the values that I have to exclude, right? So it's all reals except x can't equal 0 and it can't equal 5 because those are the values that would cause me to divide by 0, and that's a rule that we can't break, right? What about this time vertical asymptote? Where's there going to be, Vanessa, where's there going to be a vertical asymptote? At x equals what?
-5.
-5, good. Because that's a 0 of the bottom only, not the top, right? Good. Okay, we get an x-intercept at where? 1, because that's a 0 of the top only, right? And what about a hole? At where? 0. And why is that? Because it's a 0 top and bottom, right? And now think about this in terms of numbers, right? That's a good way to kind of, oftentimes if you think numbers, it simplifies things. So an x-intercept at 1, if I plug in 1, I'm going to get what would I get? I would get back 0 on the top divided, because I get 1 times 0, right? Let's do it this way. I want to make sure we, f of 1 gives us back 1 times 0 divided by 6 times 1. Well, if I simplify that, 1 times 0 is 0, 1 times 6 is 6. So we get 0 divided by 6. Well, 0 divided by a number is what? Always 0. Yeah, we get an answer back of 0. Okay, vertical asymptote at -5. How come? Because f of -5 gives us -5 from the first factor on the top. The next factor gives us -6 divided by 0 times -5. Well, if I simplify, I get 30 divided by 0. Can't do that, right? A number divided by 0 is not allowed. And what does it really mean? It means infinity, right? It means we're getting something infinite back. So that's a vertical asymptote. And then finally, the whole at 0, if I evaluate this function at 0, what's happening? Well, if I evaluate it at 0, I'm getting 0 times -1 over 5 times 0, which is 0 over 0. And that one is a little perplexing. I mean, that one's a little bizarre. In calculus, we'll talk a lot more about this, and that is what we call in calculus an indeterminate form. We don't know. We have to do more work to see. Okay? It could be lots of different things, but we don't know yet. Okay. So how about, what's that I want to do? There we go. What about one like that? I think that we didn't quite get to one like that, did we? Pretty sure. Okay, I'd like you to try to find all that information for this one. So I want the zeros of the numerator and denominator. And then also, while you're at it, let's answer the questions. What's the domain? Vertical asymptotes, poles, and x-intercepts. Go. Okay, what's our thinking about this one then? Get a chance to work on this a little bit. What's our thinking here? So we gotta be able to fill in that same box. Let me grab, oops. There we go. Ah, come on. Okay, we gotta be able to fill in that stuff, right? Okay. So, what do we got? Zeros of the numerator. What do you think? Brooke, how am I gonna find the zeros? Oh, what am I doing? I already have those up there. I remember what I was doing here. How am I gonna find the zeros of the numerator? What do we get? I mean, that's not very helpful form, is it? If I wanna set the top equal to 0, what would I do? Because that's really all we're doing, right? We're finding where does the numerator equal 0. So to find the answers to that question, we would just set x squared minus 2x minus 8 equal to 0 and solve. What are my options? That's just a quadratic equation, right? So what are my options for solving a quadratic equation? I could use the quadratic formula, right?
For the differences squared.
I could use completing the square. We haven't done that in quite a while. But there's a really easy way I could maybe do this, right? We always want to first see if it factors, right? Magic numbers, exactly. Okay, so what would the magic numbers be here? What would they have to multiply to and add to? Let's kind of remind ourselves. We haven't done this in a little while. Multiply to -8, add to -2. Okay, so what would those be? -4 and 2. And while we're at it, why don't we just put the factors on the top like we had last time? So we end up with an x minus 4 times x minus 2. And that's going to make finding the zeros at the top pretty easy. Well, let's go ahead and take care of the bottom also. Can we factor the bottom? What would the magic numbers have to multiply to in the bottom? 12. And add to -7. Okay, so we know we get x's there, right? So let's think about the signs. If they're going to multiply to a positive and add to a negative, what would the signs have to be? Both negative. Okay, and what would the numbers be? 3 and 4. Okay, so now this looks fine, right? Now this is just like the problems we've done here for the last half an hour, right? Okay, so Brooke, I'm going back to you here then. What are the zeros of the numerator? And factoring it was really helpful. What do you think? 4 and 2, yeah. Okay, those are the values. If I set the top equal to 0 and solve, that's what I get, right? The zeros of the factors. So x is equal to 2 and x is equal to 4. Zeros of the denominator. What do you think? Zeros of the denominator. Okay, what do you think? Ideas. What do we got? Bailey, can tell me. 3 and 4. Good. Okay. Let's see. Mallory, what's the domain then? Then we start with all real numbers, but are there any we'd have to exclude? Well, positive 3 and 4, right? Yeah, good, because those are the zeros of the denominator. So that's the ones we exclude from the domain. So x cannot equal 3, x cannot equal 4. Okay, vertical asymptotes. Martin, where are we going to get a vertical asymptote? Okay, so at 3 and 4? Right. No, not both. Only one of them. How come is the question, I guess.
I'm not entirely sure.
Okay.
I don't remember.
Okay, helps out. Yes.
Is it negative 3 or positive?
Positive 3, because x minus 3 equals 0 when x equals 3, right? Oh, did I? No, that's right. That's right. right? Is that the question? Am I missing something here?
For the vertical thing, because I know, don't you?
Oh, I see.
Because that's included in both the numerator and the denominator.
Right, okay, so you're saying, I got you, I understand what you're saying. So you're suggesting that it's 3, and it is, right, it's 3. And the reason being, go ahead and say it again, you're right. Vanessa.
4 is being shared in the numerator and denominator.
Okay, good, good. 4 wouldn't work because 4 is a shared 0. Vertical asymptotes occur at exclusive zeros of the bottom, right? So the only value up here that is only a 0 of the denominator is 3. So we get a vertical asymptote at x equals 3. Question?
So like if they're like the same in the numerator, or if there's like a shift in the numerator and the denominator, they just cancel each other out.
Well, okay, so algebraically, and that we'll take a look at that in a second. Algebraically, they do, but what does that mean is actually happening there? If we have a shared 0, do you remember what that creates on the graph? Would you?
A hole.
It's a hole. Good. So we have a hole at x equals 4, right? And x intercepts where? What do you think? X intercepts. Okay, the
Just
4
two.
is already, yeah, just 2, because 4 is already a hole, right? So we'd have an x-intercept at x equals 2. Now let's look at the graph of this, and here's the one last thing I want to reinforce, and then I think this is probably about wraps it up, right? So we see that if I graph the function x minus 4, because let's graph this in factored form, x minus 4 times x minus 2 over x minus 3 times x minus 4. Okay, so look what we get here. We have a vertical asymptote at, as expected, at 3, right? If I graph the line x equals 3, there's our vertical asymptote. It fits. How about the hole? Well, if I evaluate the function at 4, what am I going to get? Undefined, right? So there must be a hole in the function. Okay, so there's a hole in the function at 4, which means that right there, if I really want to draw this accurately, Desmos isn't going to do it. Desmos is going to emit one little pixel, but you can't see one pixel. So we would make that bigger, put an open circle there, which indicates there's a hole in the function, right? Okay, here's the thing though. What if I were to algebraically, just from yesterday, see if you can remember how this works. If I were to algebraically cancel the factors x minus 4. So I'm going to graph the function, a new function down here. Let's graph the function g of x. How about? G of x equals x minus 2 divided by x minus 3. Well, they line up perfectly. They're the same thing, right? What's the only difference? Yeah, there's no hole in g of x. G of 4 is defined. It's 2. You get that? That's pretty interesting. So algebraically, if we cancel those factors, what have we done? We've created a simpler function, but we changed it in one way. We filled in that hole, right? So let's come up with a strategy then. What if we wanted to do a sketch of this original function before we cancel any factors? What would be the easiest way to graph the shape of the function? Would I want to use it in that form or that form? Wouldn't that be a lot easier, right? That looks easier to me than that does, right? You get it? So we could graph the shape of the function. They're the same. They have the same vertical asymptote, right? But what's the one thing I would have to add to the simple black function to get the correct red function back? We'll have to add that hole, don't I? Right? I have to add the hole because in this function I can see that 4 is actually needs to be excluded from the domain, but it doesn't look like it does there, right? You get the idea? If we take the really simple example that's kind of, I mean, I know that seems, it seems really simple what I'm saying there, like, duh, but this is a really sophisticated idea in calculus, for example. If I want to graph this function, that looks kind of complicated, x squared over x, right? It looks like this rational function, you know, but if I algebraically simplify it, let's just call that g of x. What does this function become if I simplify it algebraically? What is x squared over x? Well, you guys know that. Come on, that's x to the 2 over x to the 1. What is that? X, yeah. It's x, right? So I can graph the function. I can graph the function y equals x. That's just a line through the origin with a slope of 1, right? So that's easy. But if this is supposed to represent f of x, what's the domain of f of x? X cannot equal what? 0, right? X cannot equal 0 because I do have an x on the bottom. So it's easy to get the shape of the graph from the simplified one. But if I'm graphing the yellow function, what do I have to go back and include? There's just one little thing I got to tweak. Got to put a hole, right? I got to put a hole at, oops, oh, that's not it. At there, right? There we go. So I got to put a hole right there, right? That is, I know that seems really simple, but that is a huge deal in calculus. It's called exploiting two functions that agree at all but one point. When we want to take hard limits, that's what we do. We're going to simplify a function, but remember that we still have that hole there, right? Okay. Okay, what are we out of here? 25? You know what? I'm going to do one last thing for you guys, and then Monday I'll give you a whole workbook. Which, go back to the other one we're looking at? Yeah.
Why is there a second hole? Or, I don't know.
That one?
The other one. Or yeah, that one.
That one, okay. Yeah.
What's the second hole?
Okay, there isn't a second hole.
Oh, why was there
Like looking on here,
that's not the
that's the one we were just looking at, right?
what you drew? There was 2 holes on it. I don't know why.
Oh, I got you. Okay. Maybe one of them was left over because there should have only been one at 4.
You drew at 4 and then there was one at the bottom.
That must have been left over from a different one or something. Yeah.
Senior pick.